Physics Part 200. If white light passes through a low pressure gas and the spectrum of the white light is then analyzed, it is found that the light of certain wavelengths is missing. In their place are dark lines. These types of spectrum is called absorption spectrum. One is shown in figure as the white light passes through the gas, some electrons absorb energy and make transitions to higher energy levels. The wavelengths of the light they absorb correspond exactly to the energies needed to make the particular upward transitions. When these excited electrons return to lower levels, the photons are emitted in all directions, rather than in the original direction of the white light. Thus, some wavelengths appear to be missing. It follows that the wavelengths missing from an absorption spectrum are those present in the emission of spectrum of the same element. This is illustrated in the figure 2. The electromagnetic spectrum, visible light is just a small region of electromagnetic spectrum. All electromagnetic waves are transverse waves consisting of electric and magnetic fields which oscillate at right angles to each other and to the direction in which the wave is traveling. This is illustrated in the figure. Relation between an absorption spectrum and emission spectrum of the same element: A. Spectrum of white light. B. Absorption of spectrum of element. C. Emission of spectrum of same element. Oscillating electric and magnetic fields in electromagnetic waves. Electromagnetic EM waves show all the properties common to wave motion. They can be reflected, refracted, and diffracted. They obey the principles of superposition and produce interference patterns. But they are transverse waves. They can, in addition, be polarized. In a vacuum, all electromagnetic waves travel at the same speed, 3.00 into 10⁻⁸ meters per second. The complete electromagnetic spectrum is divided into a series of regions based on the properties of electromagnetic waves in these regions. As illustrated in the figure, it should be noted that there is no clear boundary between regions. We've got an example for you. Calculate the wavelength of the radiation emitted when the electron in a hydrogen atom makes a transition from the energy level at -0.54 into 10⁻⁻18 joule to the level at -2.18 into 10⁻⁻18 joules. Planck constant H is 6.62 into 10⁻⁻34 joule per second. Speed of light c is 3.00 into 10⁻⁸ meter per second. Here delta E is equal to E2 minus E1, minus 0.54 into 10⁻⁻18, minus 2.18 to 10⁻⁸18 is equal to 1.64 into 10⁻⁻18 joules. Using lambda as hc over delta E, lambda is equal to 6.62 into 10⁻⁻34 into 3.0 into 10⁻⁸8 over 1.64 into 10⁻⁻18, which is equal to 1.21 into 10⁻⁻7 meter, and the answer is 121 nanometer. Now it's your turn. Calculate the wavelength of the radiation emitted when the electron in a hydrogen atom makes a transition from energy level at -3.4 into 10⁻⁻18 joule to the level at 8.5 into 10 power raised to minus 18 joule.